Imagine exploring a sprawling, bustling metropolis, right? But you're only allowed to see the streetlights. You can't see the skyscrapers, you can't see the asphalt, and you definitely can't see the ground under your feet.
Yeah, you're just looking at these suspended grids of light hanging in the dark.
Exactly. And you only know the city is actually there because those lights are arranged in very specific patterns. They curve around invisible obstacles and, well, they don't just fall down into the abyss. That is basically our relationship with the universe right now.
It really is. I mean, it's a humbling reality.
We're living in a cosmos where the overwhelming majority of mass is just entirely invisible to us. So today, we aren't just mapping the streetlights, we are hunting for the dark architecture underneath them. We're doing a deep dive into the most profound physical mystery in modern cosmology.
And we have a lot of ground to cover.
Oh, absolutely. We're tracing a path from, 19th century blackboard sketches all the way to the mind-bending discoveries pouring out of the James Webb Space Telescope in LIGO in late 2025.
To contextualize the sheer scale of that invisible architecture, we really have to look at the mass-energy budget of the universe. If you tally up everything that interacts with electromagnetism, every star, every planet, the vast nebulas, supermassive black holes, and you sitting there listening to this, it accounts for a staggering 5% of the cosmos.
Wait, just 5%? That's everything we've ever seen or touched?
Everything. The rest of the universe is functionally a phantom. About 68.2% is dark energy, which is driving the accelerated expansion of space.
Right.
And the remaining 26.8% is the subject of our focus today. Dark matter. It is the dominant gravitational framework of reality. We are merely, well, a trace element, just a faint dusting of luminous material clinging to this massive unseen structure.
Okay, so if we're going to hunt for this framework, we need to pin down exactly what we mean when we say dark matter. The source material leans heavily on a technical definition here.
Right, we have to define its boundaries.
It's a substance that does not emit, reflect, or absorb any frequency of electromagnetic radiation. It only communicates with the rest of the universe through gravity. So it essentially acts as the scaffolding.
Yes, the cosmic web. When we look at cosmological simulations, we don't see an even soup of matter. We see this vast, sprawling web.
With dense superclusters connected by narrow filaments, right?
Exactly. And the visible galaxies are essentially just glowing condensation trapped in the gravitational nodes of that web. But, the structural distribution is wildly non-uniform.
How so?
Cosmologically, dark matter dictates the macrostructure of the whole universe. It anchors the galactic halos. But locally, down here on our scale, its density is absolutely minuscule.
So it's not like there's a huge clump of it sitting in my living room.
Not at all. If you were to draw a giant sphere around our solar system, extending all the way out to the orbit of Neptune, the total mass of the dark matter enclosed in that entire volume would only amount to roughly 10 to the 17th kilograms.
Which sounds like a big number, but in space terms?
In space terms, that is the mass of a single moderately sized asteroid. It is incredibly diffuse on the human scale, but because it permeates the entire galactic volume, its cumulative mass governs the whole galaxy's rotation.
Okay, let's unpack this a bit. To understand it fundamentally, cosmologists look at how it behaves dynamically under the expansion of the universe.
Right. What's fascinating here is how we define matter mathematically. It's any substance whose energy density dilutes as the inverse cube of the cosmic scale factor, often written as invertown to the -3.
Because the expansion of space is purely a volumetric increase. Like if you take a certain number of particles and stretch the 3D space they occupy, the volume goes up. So the density drops by that exact cubed factor.
Precisely. But the sources draw a sharp distinction between how matter scales and how radiation scales. Radiation dilutes as a minus to the -4.
Wait, where does that extra power of 4 come from? Why does light dilute faster than matter?
Yeah, the underlying thermodynamics of that difference is critical. Radiation, like the cosmic microwave background photons streaming through you right now, experiences that volumetric dilution, giving us the inverse cube.
Right, the spreading out.
But space itself is expanding, which means the actual physical wavelength of every individual photon is being stretched as it travels.
Ah, so it's losing energy on top of being spread out.
Exactly. This stretching shifts the light toward the red end of the spectrum, lowering its quantum energy. That additional loss of energy per photon contributes a fourth power to the dilution.
Okay, but dark matter doesn't experience that radiation redshift.
No, it doesn't. Its kinetic energy might cool, but its rest mass energy remains absolutely fixed. And this immediately separates it from the cosmological constant, or dark energy, which doesn't dilute at all. Dark energy's density remains rigidly constant regardless of how much the universe expands.
So dark matter behaves strictly like ordinary mass under cosmic expansion. It's just completely invisible. Okay, so if it's this ghostly, non-interacting substance that only amounts to an asteroid's worth of mass in our solar neighborhood, how did anyone ever figure out it existed? I mean, we aren't starting with modern orbital telescopes here.
No, the historical breadcrumb trail begins way back in 1884 with Lord Kelvin.
Really? That early?
Yeah, he was giving lectures in Baltimore and decided to try and estimate the mass of the galaxy using the velocity dispersion of stars near our sun. He was applying classical mechanics to the Milky Way disk.
So he's basically watching how fast stars are moving to weigh the galaxy.
Right. He measured the vertical velocities of stars oscillating through the galactic plane. By calculating how fast they were moving and how far they drifted before gravity pulled them back down, he deduced the total gravitational potential of the local disk.
And I'm guessing the math didn't add up with the stars he could see through his telescope.
Not even close. His calculations indicated that the mass required to generate that gravitational pull vastly exceeded the mass of the visible stars. He concluded that a great majority of the bodies in our galaxy might be completely dark.
Wow. And then the source mentions Henri Poincaré.
Yes, Poincaré reviewed Kelvin's methodologies in 1906 and actually coined the phrase matière obscure dark matter, though he was initially pretty skeptical of the proportion Kelvin suggested.
It's wild that the term is that old.
Yeah.
But that theoretical groundwork kind of just sat idle for decades, right? Until Fritz Zwicky pointed his telescope at the Coma Cluster in 1933.
Enter Zwicky. He was a brilliantly maverick astrophysicist at Caltech. And he didn't just look at local stars, he looked at an entire grouping of massive galaxies.
And to figure out the mass of the Coma Cluster, he used something called the virial theorem.
Right, which is essentially a way to balance the books between kinetic energy and gravitational energy in a stable system. The theorem states that for a stable self-gravitating system, the total kinetic energy has to equal half the total gravitational potential energy.
So if you know how fast the things inside are moving, you know how much gravity is needed to keep them from flying away.
Exactly. Zwicky used spectroscopy to measure the Doppler shifts of the galaxies near the edge of the Coma Cluster. By looking at how the spectral lines shifted toward the red or blue, he could calculate their line-of-sight velocities.
And when he crunched the numbers.
The numbers were staggering. The galaxies were moving so violently that, by all rights, the cluster should have flung itself apart billions of years ago.
So the gravitational potential required to hold those fast-moving galaxies together meant the cluster had to have way more mass than he could see.
He estimated about 400 times more mass than what he could account for by adding up the visible starlight. The visible mass was essentially a rounding error compared to the gravitational glue holding the system together.
400 times. I mean, I know Zwicky's exact math was off because the Hubble constant of the 1930s was highly inaccurate, but his fundamental conceptual framework was completely flawless.
Yes, he called this missing mass Dunkel materia.
But, you know, one localized observation of a galaxy cluster doesn't force the whole scientific consensus to rewrite the laws of physics. The undeniable breaking point came later, with galactic rotation curves in the 1970s.
Yes, Vera Rubin and Kent Ford. They started mapping spiral galaxies, looking edge-on at the optical spectrographs of their spinning disks.
And what they were expecting to see was a standard Keplerian decline, right? Like how our solar system works.
Exactly. In our solar system, the vast majority of the mass is in the sun. Consequently, Mercury orbits at a blistering 47 kilometers per second just to avoid falling into the gravity well, while Neptune drifts along at barely 5 kilometers per second.
Because the gravitational field weakens with distance.
Right. So when astronomers looked at spiral galaxies, the optical light was intensely concentrated in the central bulge. Therefore, they logically assumed that the stars on the sparsely populated outer fringes should orbit much slower than the stars near the dense core.
But they didn't. When Rubin plotted the velocities, the rotation curves went up, and then they just flatlined.
The stars at the extreme edges of the Andromeda galaxy were whipping around the center just as fast as the stars in the inner disk.
I always like to picture this as the merry-go-round problem. If you spin a playground merry-go-round at a super high speed, The kids clinging to the outer edge experience massive centrifugal force and should fly off into the dirt.
That is a perfect analogy.
If they don't fly off, either gravity works differently in the playground, or there are invisible seatbelts holding them in. Zwicky and Rubin found the invisible seatbelt.
They did, and soon after, the radio astronomers found them too, probing even further out into the dark.
Right, looking past the visible starlight entirely.
Yeah, specifically mapping the 21-centimeter emission line of atomic hydrogen. In the late 70s, Albert Bosma used a radio telescope to track neutral hydrogen gas extending far beyond the optical edges of the galaxies.
And what happened to the rotation curves out there?
They remained absolutely flat out to tens of kiloparsecs into the void. This couldn't just be dismissed as a localized optical illusion or dust obscuring the light. The universal constant was that every galaxy is embedded in a massive spherical halo of unseen mass.
Okay, so if the merry-go-rounds are universally strapped with invisible seatbelts, we have to look beyond just the spinning disks. I mean, a single anomaly could be an observational error, but the evidence for dark matter is basically a mountain built from completely independent fields of physics, all pointing at the exact same ghost.
Exactly. Let's start with velocity dispersions in systems that don't spin.
Like elliptical galaxies.
Right. Elliptical galaxies and globular clusters lack a neat, flat rotation disk, but the stars swarming inside them are moving at kinetic velocities that violently violate their visible mass budget.
And then you step up to the grandest scale of general relativity. Gravitational lensing. This is the one that always blows my mind.
It's beautiful physics.
Yeah.
Gravitational lensing completely removes the need to measure stellar velocities. According to Einstein, mass dictates the curvature of space-time.
So a huge mass literally bends the space around it.
Yes. So when we observe a massive foreground galaxy cluster like Abell 1689 sitting between Earth and a distant background quasar, the mass of that foreground cluster bends the space-time around it. It acts as a colossal cosmic lens.
And in the strong lensing regime, the light from the background quasar gets severely distorted, right? Creating those sweeping magnified arcs or even multiple mirrored images of the exact same object.
Exactly. And by mathematically reconstructing the exact geometry required to bend the light into those specific arcs, we can derive a highly precise mass for the cluster doing the bending.
And I'm guessing that mass calculation doesn't match the visible stuff.
It consistently dwarfs the baryonic mass of the cluster's visible gas and stars.
And it isn't just the spectacular visually obvious arcs either. The source mentions weak lensing data too.
Yes, weak lensing is where astronomers measure the minute statistical shearing of thousands of background galaxies. It maps perfectly onto the massive dark matter halos. The mass is absolutely there, distorting space-time, even when there's nothing to see.
Okay, but to me, the most profound evidence requires looking all the way back to the structure formation of the early universe, because the timeline of the cosmos simply doesn't work without dark matter.
No, it falls apart. If we connect this to the bigger picture, the early universe was a chaotic, radiation-dominated inferno. Ordinary matter, primarily hydrogen and helium nuclei, was fully ionized and coupled to the intense bath of photons.
Creating what cosmologists call the baryon photon fluid.
Right. So whenever gravity attempted to pull the ordinary matter together into a clump, the immense radiation pressure would violently push back, basically washing out the density fluctuation.
So if ordinary matter was the only substance in the universe, it wouldn't have been able to begin collapsing into gravity wells until the universe expanded and cooled enough for the photons to let go.
Exactly, an event known as recombination.
But if ordinary matter had to wait hundreds of thousands of years for recombination just to start clumping, there mathematically wouldn't have been enough time between the Big Bang and today for those tiny ripples to grow into the supermassive galaxy clusters we observe. The cosmic timeline is just too short.
Precisely. This is where dark matter provides the essential head start. Because dark matter possesses no electromagnetic charge, it is entirely immune to radiation pressure.
So it wasn't stuck in that tug-of-war.
Not at all. While the baryons were trapped in that chaotic tug-of-war with photons, the dark matter was freely, quietly collapsing under its own gravity, carving deep gravitational potential wells into the fabric of space-time.
Digging the foundations before the visible universe was even allowed to start building.
Beautifully put. When recombination finally occurred and the ordinary matter was freed from the radiation, it found these massive, pre-existing dark matter sinkholes waiting for it. The baryons simply fell into the dark matter architecture.
And that intense tug-of-war left a literal fingerprint on the universe. We can actually see it in the cosmic microwave background, the CMB.
We can. Satellites like WMAP and Planck mapped the relic radiation from the Big Bang, revealing temperature anisotropies fluctuations of just a few parts in 100,000.
The red and blue splotches on those famous oval maps.
Exactly. And when physicists run a power spectrum analysis on those splotches, they find a series of acoustic peaks.
The acoustic peaks. Okay, these are the most rigorous, mathematically unforgiving proof of dark matter's existence, right?
Yes, those peaks represent the actual sound waves oscillating through the primordial baryon photon fluid. Gravity pulled the fluid into dense, hot compressions, and radiation pressure forced it into rarefactions or expansions.
So the first, highest peak in the power spectrum represents the fundamental compression. The largest sound waves that had exactly enough time to reach maximum density right before recombination froze them in place.
Correct. But it is the relationship between the subsequent peaks that reveals the universe's true composition.
Because the third peak tells a completely different story than the first two.
Exactly. The odd-numbered peaks represent compression phases, driven by gravity, while the even-numbered peaks represent the rarefaction phases, driven by the radiation pressure bouncing back.
Right. The bounce.
If the universe only contained regular baryonic matter, the gravity driving the compressions would be strictly limited. But the third peak, which is a compression peak, is disproportionately high relative to the second peak.
So that mathematical asymmetry proves the existence of a massive gravitational driving force that does not experience the outward bounce of radiation pressure.
You nailed it. It isolates the density of non-interacting matter with excruciating precision. The CMB proves dark matter was dictating the thermodynamics of the cosmos hundreds of thousands of years before the first star ever ignited.
Okay, so what does this all mean for the temperature of dark matter? Because the source categorizes it as hot, warm, or cold. But we aren't talking about thermal heat here, are we?
No, we are talking about kinetic velocity and something called the free streaming length.
Which is basically how far a dark matter particle could travel in the early universe before the cosmic expansion sapped its momentum.
Right. If dark matter particles were moving at relativistic speeds, close to the speed of light, we classify them as hot dark matter. A classic example of a hot candidate is the neutrino.
Because neutrinos have a tiny rest mass, they're neutral, and they travel incredibly fast.
Exactly. But if the universe were dominated by hot dark matter, its immense free streaming length would mean these fast-moving particles would effortlessly zip right out of small gravitational wells, essentially smearing out any small-scale density fluctuations.
So they wouldn't be able to form small galaxies first.
Right. In a hot dark matter universe, the first structures to form would be colossal, super-cluster-sized sheets or pancakes, which would only much later fragment into individual galaxies.
But we know that's fundamentally backward, right?
Yeah.
When JWST and Hubble look out to the highest redshifts, the actual dawn of the universe, they don't see massive superclusters fragmenting.
No, they see tiny, chaotic proto-galaxies that merge and build from the bottom up. Small structures formed first.
Therefore, the bulk of dark matter couldn't have been moving at near light speed. It must have had a very short free streaming length. It has to be cold, dark matter, which immediately disqualifies the neutrino from being the primary constituent of the galactic scaffolding.
Neutrinos undoubtedly exist, and they do contribute a minute fraction to the total mass budget. But the macro structure of the universe demands a slow-moving, massive particle.
Which forced physicists to ask, if it's slow, massive, and invisible, could it just be ordinary, non-luminous matter that we simply can't see? Like rogue planets, cooled brown dwarfs, primordial black holes, or neutron stars just drifting in the halo.
Yes, this hypothesis was categorized under the acronym MACHO's Massive Compact Halo Objects.
It's definitely the most intuitively comforting answer. Like, the universe isn't full of exotic, unknown physics. It's just full of dark rocks and dead stars.
It is comforting, but the MACHO hypothesis totally collapses under the weight of Big Bang nucleosynthesis.
BBN, the fusion happening in the first 3 minutes of the universe.
Exactly. Big Bang nucleosynthesis models the exact nuclear fusion rates occurring in those first 3 minutes. The temperature and density of the cosmos during that brief window dictated the precise ratio of light elements forged, specifically the abundance of hydrogen, helium-4, deuterium, and lithium-7.
And the amount of deuterium in the universe is hypersensitive to the total density of baryons ordinary matter.
Extremely sensitive. If you attempt to stuff the universe full of enough ordinary baryonic matter to account for the 26.8% dark matter deficit, the extreme density in those first 3 minutes would have caused nearly all the deuterium to fuse into helium.
Oh, wow. So the primordial abundances we observe today rigidly cap the total allowable baryonic matter at roughly 4 to 5% of the critical density.
Yes. The math absolutely forbids MATA shows from solving the dark matter problem.
And observational astronomy backed up the nuclear math. Right? We pointed telescopes at the Magellanic Clouds for years, waiting for microlensing events.
Waiting for a rogue macho in our galaxy's halo to drift in front of a background star and briefly magnify its light through gravity.
But the surveys only found a handful of events, nowhere near enough to account for the halo's mass.
Yeah.
They systematically ruled out objects ranging from subplanetary masses all the way up to heavy stellar remnants.
They did. But if we need a singular, visceral piece of evidence that permanently severs dark matter from ordinary baryonic mass, we have to look at the bullet cluster.
Oh, man. The bullet cluster is the ultimate smoking gun.
It really is. Formerly designated 1E065756, we are observing the immediate aftermath of a hyperviolent cosmic collision between two massive galaxy clusters.
Now, in a galaxy cluster, the galaxies themselves are actually relatively sparse. The vast majority of the normal baryonic mass is held in the intracluster medium, the superheated clouds of plasma and intergalactic gas between the stars.
Right, so when these two clusters slammed into each other, the individual galaxies mostly passed right past one another like ships in the night because the space between stars is so vast.
But the massive gas clouds collided head-on.
Yes. They interacted electromagnetically. They generated immense ram pressure, creating a colossal shock wave, heating up to millions of degrees and emitting blazing X-rays. Crucially, the gas physically decelerated.
The baryonic mass got bogged down in the center of the collision zone.
But the gravity did not.
This is the crazy part. By meticulously analyzing the weak gravitational lensing of background galaxies located behind the bullet cluster, astrophysicists mapped the exact topography of the cluster's mass.
And the maps revealed that the overwhelming majority of the mass was not located in the center with the X-ray emitting hot gas. The mass was separated into two distinct lobes flanking the collision zone.
I always visualize the bullet cluster like this. It's like watching two massive flocks of birds flying directly into each other. The birds represent the baryonic gas. They hit each other, squawk, tangle up, and slow down into a chaotic, concentrated mess in the middle.
Right.
But their shadows on the ground below, representing the dark matter, just glide perfectly forward, passing right through each other without the slightest friction, entirely detaching from the birds.
The center of mass and the center of the visible plasma are physically disjointed. And this detachment is exactly why the bullet cluster is considered absolutely lethal to theories of modified gravity.
How so? Because if gravity is just tweaked, it should still point to the gas, right?
Exactly. If the dark matter anomaly is merely a misunderstanding of Newton or Einstein, if gravity is just inherently stronger at large distances, then that amplified gravitational pull must still be anchored to the actual physical matter present.
Because you cannot modify the equations of gravity to point toward empty space.
You can't. The center of gravity would have to align perfectly with the hot X-ray gas because that is where the mass is. The gravitational lensing in the bullet cluster maps an enormous mass sitting in regions where no ordinary matter exists. It proves that the shadow is cast by a real, physical, non-interacting substance.
Okay, so if the shadow is real, and it's not made of protons or neutrons, we crossed into the realm of new particle physics. And for the last 30 years, the global physics community has heavily banked on microscopic suspects to explain the macroscopic universe.
The two towering candidates have been WIMPs and axions.
Let's dig into the WIMP first. The weakly interacting massive particle. The source notes a target mass of around 100 giga-electron volts. Why did this specific hypothetical particle absolutely dominate the funding and theoretical landscape for 3 decades?
It was driven by an extraordinary theoretical coincidence known as the WIMP miracle.
A miracle. That sounds dramatic.
Well, in the violently hot, dense epoch of the early universe, particles of all kinds were in thermal equilibrium, constantly colliding, annihilating, and being newly forged from pure energy.
Okay.
As the universe expanded, the ambient temperature dropped. Eventually, the thermal energy fell below the threshold required to create massive WIMPs. The existing WIMPs continued to collide and annihilate each other, dropping their population drastically.
But the universe was still expanding.
Right. The rate of expansion, governed by the Hubble parameter, eventually outpaced the annihilation rate. The particles became too spread out to find each other, and their abundance essentially froze out.
And the math of that freeze-out is where the miracle happens. Because if you calculate the interaction cross-section required for a particle to freeze out at the exact density needed to leave behind, 26.8% of the universe's mass today. The equations demand a particle that interacts exclusively via gravity and the weak nuclear force, with a mass right around the electroweak scale, roughly 100 GeV.
It was a mathematically beautiful convergence. And what made it totally irresistible to the physics community was that entirely separate theoretical frameworks, constructed to solve deep structural flaws in the standard model of particle physics, independently predicted this exact kind of particle.
Like supersymmetry?
Exactly. Supersymmetry, a theory proposing a heavier superpartner for every known subatomic particle, naturally churned out stable, weakly interacting particles like the neutralino. These particles possess the precise mass and cross-section required to be the dark matter wimpy.
It really felt as though cosmology had handed particle physics a lock, and particle physics already had the exact key sitting in its pocket.
It did, but on the complete opposite end of the mass spectrum, we have the axion.
Right. If a WIMP is a heavyweight, an axion is a featherweight. It's an ultralight boson originally theorized in the 1970s to solve a completely different crisis, the strong CP problem in quantum chromodynamics.
The strong CP problem is a glaring theoretical friction. The mathematics of quantum chromodynamics, which is the physics governing quarks and the strong nuclear force, suggests that the strong force should violate charge parity symmetry. It should treat matter and antimatter differently.
But it doesn't.
No. Highly sensitive experiments looking at the electric dipole moment of the neutron show absolutely zero violation. To solve this, physicists Roberto Pichai and Helen Quinn introduced a new dynamic scalar field that naturally suppresses this violation, driving it mathematically to zero.
And in quantum field theory, when you introduce a new field, the ripples or excitations in that field manifest as a particle.
Precisely. The axion. And if the axion possesses a mass above 5 microelectron volts, which is infinitesimally small, we're talking 100 billion times lighter than an electron, it would have been produced non-thermally in staggering, incalculable quantities in the early universe.
Because they are so light, they would act more like a coherent classical wave oscillating through the cosmos than individual billiard ball particles.
Right. They are cold, incredibly stable, and weakly interacting. A flawless dark matter candidate that, just like the WIMP, solves a profound nuclear mystery while simultaneously fixing the cosmological mass deficit.
Okay, here's where it gets really interesting,
Yeah.
but also a little frustrating. If the universe is flooded with an ocean of axions or a swarm of WIMPs, it forces us to ask a structural question. Why doesn't this stuff ever form dark planets or dark stars?
That's a great question.
If gravity pulls it together into massive galactic halos, why does it stop there? Why doesn't it condense into highly concentrated compact objects?
It comes down to the mechanics of particle aggregation and energy dissipation. For any physical system to collapse into a dense, tight structure, it must possess a mechanism to shed kinetic energy.
Like regular gas clouds forming stars.
Exactly. When a massive cloud of ordinary hydrogen gas begins to collapse under its own gravity, the gas particles accelerate. As they speed up, the internal temperature and pressure of the clouds skyrocket. If that heat cannot be released, the outward thermal pressure eventually balances the inward gravitational pull, and the collapse halts.
But ordinary matter can cool down. Electrons transitioning between atomic orbitals emit photons. The gas radiates away its kinetic energy as electromagnetic light and heat, lowering the internal pressure and allowing gravity to crush the matter down into dense stars and planetary cores.
But dark matter is completely blind to electromagnetism. It cannot emit a photon. It cannot radiate away its heat.
So if a massive swarm of WIMPs falls toward the center of a gravity well, they accelerate and pick up tremendous kinetic energy.
And because they can't bleed off that energy through radiative cooling, they simply zoom straight through the center of the well and fly right back out the other side. They just oscillate indefinitely.
They're trapped in a diffuse, puffy halo, physically incapable of settling down into complex, tightly bound structures.
This inability to lose energy is what maintains the massive scaffolding of the cosmic web. But it also presents a monumental experimental frustration. If these particles cannot shed energy to interact tightly, catching them in a detector requires monumental technological leaps.
And decades of those technological leaps searching for WIMPs and axions have yielded an excruciating silence. The theoretical parameters have been squeezed tighter and tighter over the years.
Which brings us to the profound paradigm shift recorded in late 2025. The realization that we might have been looking at the wrong end of the size spectrum entirely.
I love this part. We transition from the microscopic to the macroscopic. The plot twist of 2025, primordial black holes.
PBHs aren't a totally new idea. Yakov Zeldovich and Stephen Hawking played with the math back in the 60s and 70s. But we have to clearly differentiate a primordial black hole from a standard stellar black hole.
Right, a normal black hole is the end state of stellar evolution. A massive star burns through its nuclear fuel, the outward radiation pressure stops, and the core collapses under its own immense gravity.
Because stellar black holes require a star to die, they are rigidly constrained by stellar physics. The Tolman-Oppenheimer-Volkoff limit dictates the maximum mass of a neutron star, and the physics of supernova collapse dictates that you simply cannot form a stellar black hole lighter than roughly 2.5 to 3 solar masses.
So there's a hard floor on how small they can be.
Exactly. But primordial black holes bypass stellar evolution entirely. In the first fraction of a second after the Big Bang, the universe was not a vacuum. It was a phenomenally dense, hyper-pressurized soup of radiation and fundamental particles.
And in certain microscopic pockets, the density of that primordial soup could naturally fluctuate to such an extreme that the matter simply collapsed in on itself, instantly punching a hole in space-time.
Because they formed purely from the sheer density of the early universe, they are not bound by stellar mass limits. A PBH could theoretically have the mass of Mount Everest, compressed into the size of a proton.
For decades, PBHs were considered a fringe mathematical curiosity. But the source material highlights late 2025 as a watershed moment for astrophysics. The heavy hitters of modern astronomy, LIGO and the James Webb Space Telescope, suddenly started dropping data that severely resurrected the PBH. Let's look at LIGO first.
In late 2025, the Gravitational Wave Observatory reported a candidate merger involving a subsolar mass black hole.
Which is huge. A subsolar mass merger is a catastrophic anomaly for standard astrophysics.
Completely. If LIGO detects gravitational waves emanating from a black hole that weighs less than our sun, it is physically impossible for that object to have been formed by a dying star. There is no mechanism in the modern universe to compress half a solar mass into a singularity.
So if that subsolar detection is validated, it is the smoking gun that black holes were forged in the fires of the Big Bang.
And while LIGO is listening for tiny black holes, James Webb is looking back to the dawn of time and finding absolute monsters.
Yes. JWST has been staring at the highest redshifts, less than 500 million years after the Big Bang, and discovering little red dots, highly compact, heavily reddened active galactic nuclei.
More shockingly, it's finding overmassive black holes in galaxies like UHZ1 and GHZ2. These are supermassive black holes that possess more mass than all the stars in their host galaxy combined, existing in an epoch where the universe barely had time to cool.
The timeline crisis is severe here, because standard cosmological models rely on light seeds, right?
Right. The first generation of stars, population 3 stars, ignite, die, and leave behind stellar black holes of maybe 10 or 20 solar masses. Those light seeds then spend billions of years slowly gorging on surrounding gas, accreting mass at the Eddington limit, to eventually become the supermassive behemoths we see in the center of galaxies today.
But the JWST data breaks that model. There physically wasn't enough time between the epoch of reionization and the observation of a galaxy like UHZ1 for a stellar seed to consume enough matter to reach that size.
It's impossible. The data strongly demands heavy seeds. Black holes that were born massive, practically right out of the Big Bang. Primordial black holes perfectly fit the heavy seed requirement. They would act as the instant gravitational anchors, pulling in the early gas to form those little red dots.
But wait, the historical pushback against PBHs as the primary dark matter candidate always centered on the fine-tuning problem, didn't it? The old argument was that to produce exactly enough PBHs to make up 26.8% of the universe, the initial quantum fluctuations during cosmic inflation had to be tuned to an impossibly precise degree.
Yes. If the fluctuation amplitude was slightly too small, 0 black holes form. If it was slightly too large, the entire universe immediately collapses into a singular black hole. It required too much mathematical luck.
So how do we get past that?
The fine-tuning bottleneck was shattered by profound theoretical modeling published between 2024 and 2025 regarding the thermodynamics of the early universe. Specifically, astrophysicists reevaluated the QCD phase transition.
The QCD phase transition. That's when quarks bound together, right?
Exactly. In the earliest moments, the universe was so hot that quarks and gluons roamed freely in a dense plasma. As the universe expanded and cooled, it hit a critical temperature threshold where the strong nuclear force suddenly bound those free quarks together to form hadrons, protons, and neutrons.
And that transition radically alters the pressure of the universe.
Completely. During the QCD phase transition, the equation of state, which defines the relationship between pressure and density in the cosmic fluid, experienced a sudden dramatic drop. The outward pressure of the universe momentarily plummeted.
Oh, because the pressure pushing outward suddenly dropped, the threshold required for localized pockets of dense matter to collapse inward under gravity dropped with it.
It acted as a cosmic trigger. You didn't need perfectly fine-tuned, exotic, inflationary amplitudes anymore. The universe's own natural cooling process created an era of lowered resistance, heavily favoring the mass production of primordial black holes right around the mass of our sun.
And this neatly bypasses the old microlensing surveys that supposedly ruled out PBHs decades ago. Those surveys looked at the Magellanic Clouds and assumed that if PBHs existed, they all had to be exactly the same size, a monochromatic mass distribution.
Right, like if every dark matter black hole weighed exactly 10 solar masses, then the surveys definitively proved they didn't exist.
But the physics of the QCD phase transition doesn't spit out a factory line of identical black holes. It predicts a platykurtic mass distribution.
A broad, sprawling bell curve. The thermodynamic trigger of the QCD epoch, combined with variations in the primordial density, naturally yields a massive spectrum of black hole sizes, ranging from subsolar masses up to 100 solar mass heavyweights.
So when you take the constraints of the old microlensing surveys and apply this new, wide platykurtic distribution to the data, the restrictive limits basically dissolve. A broad spectrum of TBHs easily evades the historical detection constraints and elegantly accounts for the entirety of the dark matter halo.
Exactly.
So we have this incredible realization. For 30 years, thousands of physicists have been tunneling deep into mountains, building giant vats of liquid xenon to catch tiny subatomic ghosts. And meanwhile, James Webb and LIGO might be accidentally solving the greatest mystery in cosmology by looking at the largest, most violent phenomena in the universe.
It's quite the irony.
It's like staring into a microscope for decades hunting for a microbe, only to finally look out the window and see a dinosaur standing in your front yard.
It is a phenomenal pivot in the zeitgeist of astrophysics. However, we really cannot abandon the microscopic hunt prematurely. The evidence for PBHs is compelling, but circumstantial until definitively proven.
That's true. And the particle physics community is still operating incredibly sophisticated terrestrial detectors. We need to look at how physicists are actively trying to corner these microscopic candidates on Earth through three primary vectors: direct detection, indirect detection, and collider searches.
Direct detection relies on the sheer statistics of the WIMP halo. If the Milky Way is steeped in a dark matter sea, then millions of these particles are streaming through our bodies every second.
The vast majority just pass straight through the empty space within our atoms.
But if they interact via the weak nuclear force, then very rarely one of them should physically strike the nucleus of an atom. To catch that incredibly faint microscopic recoil, physicists build detectors deep underground.
In facilities like the Sanford Underground Research Facility, SRF in South Dakota, or Gran Sasso in Italy,
the depth is essential to shield the detectors from cosmic rays, which bombard the Earth's surface and create a deafening background noise of radiation. Inside these subterranean bunkers, physicists use a few different technologies. Cryogenic detectors, like super CDMS, operate at mere fractions of a degree above absolute zero.
So when a particle strikes a silicon or germanium nucleus, the recoil generates a microscopic vibration, a phonon, that slightly raises the temperature of the crystal, and the highly sensitive electronics register it.
Exactly. But the undisputed kings of direct detection over the last decade have been the noble liquid time projection chambers. Experiments like LZ, Xenon-T, and PANDEX.
They use massive vats containing tons of liquid xenon. If a WIMP strikes a xenon nucleus, it triggers a dual-phase reaction, right?
Yes. The physical collision causes a nucleus to recoil, generating an immediate faint flash of scintillation light. We call that the S1 signal.
But the collision also knocks a few electrons loose.
Right, and an electric field drifts those electrons up to the top of the tank, where they are pulled into a layer of gaseous xenon, creating a second, brighter flash of light, the S2 signal.
And the ratio between the S1 scintillation and the S2 ionization charge is the critical metric. Ordinary background radiation, like a stray gamma ray or beta particle, interacts primarily with the electron shells, producing a high S2 to S1 ratio.
A WIMP, however, would smash directly into the dense nucleus, creating a nuclear recoil with a distinctly lower ratio. This allows the detectors to rigorously discriminate between dark matter and standard radiation.
Yet, despite operating continuously with increasing sensitivity, the 2025 status of these massive xenon detectors is a resounding silence. They haven't confirmed a single WIMP collision.
No, they haven't. What they have achieved is pushing the exclusion limits to staggering depths, proving that if WIMPs exist, their interaction cross-section is infinitesimally small.
And pushing those limits led the LZ experiment straight into a terrifying wall in late 2025. They officially hit the neutrino fog. This is the ultimate existential crisis for direct detection.
The neutrino fog represents a hard, fundamental floor to experimental physics. As you scale up the size of your liquid xenon vat, it becomes extraordinarily sensitive. Eventually, it becomes so sensitive that it starts registering coherent elastic neutrino nucleus scattering, or CEVNS.
Which is what, exactly?
Well, neutrinos are a known standard part of the universe. Billions of them pour out of the sun's nuclear furnace every second. They interact exclusively via the weak force, just like WIMPs. When a solar neutrino strikes a xenon nucleus through CEVNS, it creates a nuclear recoil that perfectly mimics the expected signature of a 10 GeV dark matter particle.
So the detector works perfectly, but the universe's own irreducible background noise is blinding it.
Yes. To pierce the neutrino fog and definitively separate a solar neutrino from a galactic WIMP, future experiments won't just need a larger vat of xenon. They will need complex directional sensitivity to prove the recoil came from the galactic halo, not the sun.
But we can't talk about direct detection without acknowledging the massive elephant in the room: the Demalbra anomaly. For over 20 years, this one experiment under the Gran Sasso Mountain in Italy has steadfastly claimed they are seeing dark matter through an annual modulation.
Yes, Demalbra uses thallium-doped sodium iodide crystals, and they aren't looking for single, highly vetted recoil events. They are looking for a statistical shift in the collision rate over time, relying on the geometry of our solar system.
Okay, so the Milky Way's dark matter halo is theorized to be non-rotating, while our solar system orbits the galactic center at about 220 kilometers per second. Consequently, we are effectively driving through a static cloud of dark matter, creating a wind of particles striking the Earth.
But the Earth is also orbiting the Sun at 30 kilometers per second. In June, the Earth's orbital velocity aligns with the solar system's galactic trajectory. We are driving head-on into the dark matter wind at maximum speed, which should increase the rate of particle collisions in the detector.
Right, and in December, the Earth is on the opposite side of the Sun, moving against the galactic trajectory. The relative speed drops, and the collision rate should dip.
And Demalbra observes exactly that. They see a robust, statistically undeniable sine wave in their data, a signal that peaks in June and troughs in December, repeating flawlessly year after year.
The profound tension in the physics community arises because no other experiment, not the hypersensitive liquid xenon tanks, nor identical sodium iodide experiments like ANIAS or cosine 100, has been able to reproduce this signal. It's a lingering, unresolved anomaly that forces physicists to constantly reevaluate their background models.
It really is a thorn in the side of the consensus.
If the underground vats are fogged out, we move to indirect detection. We look up at the stars and wait for the dark matter to reveal itself in the wild. If WIMPs are their own antiparticles, which many supersymmetric models suggest, then when two WIMPs cross paths in an incredibly dense region like the center of our galaxy, they could annihilate each other.
That pure energy conversion would spawn a cascade of highly energetic standard model particles: gamma rays, positrons, antiprotons. Space-based observatories scan the cosmos for these annihilation products.
Like the Fermi Large Area Telescope, mapping the gamma-ray sky. It discovered a pronounced, unexplained spherical surplus of high-energy gamma rays emanating from the galactic center, the famous GeV excess.
Similarly, the Alpha Magnetic Spectrometer, mounted on the International Space Station, measured an unexpected excess of high-energy positrons impacting its detectors. The data perfectly matches the theoretical energy spectra of annihilating WIMPs.
The fatal flaw of indirect detection, however, is astrophysical ambiguity. A rapidly spinning neutron star, a millisecond pulsar, can strip electrons from its surface, accelerate them in its massive magnetic field, and produce the exact same gamma ray and positron signatures.
We can't conclusively prove the radiation is coming from invisible dark matter. When known, extreme astrophysics can perfectly mimic the signal.
The source material also points out that astrophysics can be used to set limits on dark matter through stellar heating.
This is using the cosmos as a giant detector. If dark matter interacts with regular baryonic matter via scattering, it should occasionally collide with a dense degenerate matter inside neutron stars or white dwarfs.
The star's immense gravity would capture the dark matter particle, and the kinetic energy lost during the collision would deposit heat into the stellar core.
By pointing telescopes at incredibly ancient, isolated neutron stars that should have cooled down to frigid temperatures over billions of years, we can measure their thermal output. If they are inexplicably warm, dark matter heating is the prime suspect.
Conversely, finding extremely cold neutron stars places highly stringent limits on how strongly dark matter is allowed to interact with regular matter.
And there's also the fascinating mechanism of black hole superradiance, specifically tailored to hunt for ultralight axions.
Right. If you have a rapidly spinning black hole and the universe is flooded with a scalar field of ultralight bosons whose Compton wavelength happens to match the radius of the black hole, the mechanics of general relativity trigger a runaway instability.
The axions would extract angular momentum from the black hole's ergosphere, forming a massive, dense boson cloud around it, effectively breaking the black hole spin. Because we observe extremely old black holes spinning at near maximum velocity, we can definitively rule out the existence of axions in specific mass ranges.
Which leaves us with the final brute force vector, collider searches. If we can't definitively catch it underground or in space, we attempt to artificially manufacture it.
The Large Hadron Collider at CERN smashes protons together at 99.9999999% the speed of light. The kinetic energy of that collision condenses into new particles. If the collision successfully forges dark matter, we wouldn't see it. The particle would rip through the ATS or CMS detectors without interacting.
But physicists don't need to see it to know it was there. They use the conservation of momentum. If they sum up the trajectory and energy of all the visible debris flying away from the collision, the vectors must perfectly balance.
If there's a massive imbalance, if a huge chunk of momentum is seemingly missing, pointing into empty space, they know an invisible particle carried that energy away. Missing transverse energy was the gold standard signature that the particle physics community banked on.
They were supremely confident that LHC Run 3, which concluded data collection around 2025, would finally reveal the supersymmetric partners, the squarks, the gluinos, the charginos, that would lock the wimpy model into the standard model.
But the data analysis was devastating to standard supersymmetry. The ATLAS and CMS collaborations scoured the collisions and found nothing but the standard model background. They pushed their exclusion limits beyond 2.4 teraelectron volts for the mass of the gluino and well past 1 TeV for the electroaquinos.
The elegant, simple, supersymmetric frameworks that naturally predicted the WIMP miracle are effectively dead. So in the face of these exclusions, where does particle physics go? They aren't turning off the LHC.
The outline notes a heavy shift toward the darks vector. Physicists are looking for increasingly exotic, complex signatures.
If dark matter isn't a single, simple particle that cleanly interacts via the weak force, it might belong to an entire hidden dark sector, with its own complex forces and dynamics, only interacting with our standard model through tiny, heavy mediator particles.
This completely changes the signature we look for. Instead of massive missing energy, physicists at the LHC are hunting for long-lived particles. These are dark sector states that might be created in the initial collision, travel a few centimeters or even meters through the detector layers unnoticed, and then abruptly decay back into standard visible matter.
This creates displaced vertices, or disappearing tracks, where a particle track simply materializes out of thin air midway through the detector.
The 2025 ATLS limits even specifically target emerging dark jets. This envisions a scenario where a collision creates a shower of dark quarks that rapidly decay into visible hadrons in a staggered, delayed sequence, creating a chaotic, messy spray of particles completely unlike a standard quantum chromodynamics jet.
The search has become exponentially more nuanced, probing the absolute margins of the data for a tiny leak between our reality and the dark sector.
And this immense complexity, the desperate search for disappearing tracks and heavy dark mediators, forces us to step back and engage in a rigorous scientific imperative. When the world's most sensitive experiments come up empty, when the simplest mathematical models are ruled out, and when theoretical physics resorts to constructing entirely invisible realms just to make the equations balance, we must do our due diligence and listen to the skeptics.
Could Albert Einstein just be wrong? This brings us to Section 8. The skeptics and the fringe. The entire dark matter paradigm rests on a colossal assumption that general relativity, which has been flawlessly verified in our solar system and in the orbits of binary pulsars, scales up identically to the staggering distances of a galactic disk or a supercluster.
Modified gravity theories argue that we don't need a universe full of exotic, invisible particles. We just need to fix the math. The loudest alternative has historically been MOND, modified Newtonian dynamics.
First proposed by Mordechai Milgram in the 1980s, MOND postulates a fundamental tweak to gravity. It suggests that at extremely low accelerations, specifically below a threshold of about 10 to the minus 10 meters per second squared, which is the exact gentle gravitational acceleration experienced by stars at the extreme outer edges of a spiral galaxy, gravity stops following Newton's inverse square law.
Instead of dropping off rapidly, the gravitational force decays linearly, acting slightly stronger than classical physics predicts.
MOND is intensely controversial, but we have to admit it has had striking empirical successes. It doesn't just retroactively fit the data, it has predictive power. In 2020, an analysis of rotationally supported galaxies successfully detected the external field effect.
Because MOND is nonlinear, the internal dynamics of a galaxy are slightly affected by the external gravitational field of the massive universe around it. This effect was predicted by Menandi decades ago and eventually observed, demonstrating that Menandi can perfectly describe the flat rotation curves of spiral galaxies and the tight correlation between baryonic mass and rotational velocity without invoking a single particle of dark matter.
The ability to explain galactic rotation purely through baryonic mass is MOND's greatest triumph. And the existence of this theory forces the standard lambda CDM model to rigorously and continuously defend itself.
But the scientific consensus remains overwhelmingly anchored to dark matter for one intractable reason. Cosmology is not just about individual spinning galaxies. A successful theory must explain the entirety of the universe simultaneously. MOND catastrophically fails outside the galactic scale.
As we discussed earlier with the acoustic peaks in the CMB, MOND cannot explain the thermodynamic suppression of the second peak. It offers no mechanism for the baryon photon oscillations. And it utterly crumbles when faced with a bullet cluster, where the gravitational lensing is physically offset from the baryonic gas.
To address these failures, theorists developed relativistic generalizations of MOND, such as Jacob Bekenstein's TeVS tensor vector scalar gravity. But to make the mathematics of TeVS align with the CMB and galaxy cluster dynamics, theorists are often forced to inject massive amounts of unseen matter back into the equations, usually in the form of massive sterile neutrinos.
If a theoretical framework explicitly designed to eliminate the need for dark matter still requires the addition of dark matter to function on cosmic scales, it loses its philosophical and mathematical appeal.
It really does. Beyond MOND, the source material delves into truly exotic fringe theories. Scalar field dark matter, dark fluid models that attempt to unify dark matter and dark energy into a single compressible substance, or dynamical dark matter that proposes an infinite tower of particle states.
It feels, frankly, almost like magic at this point. The outline explicitly draws parallels to science fiction, mentioning dust in Philip Pullman's His Dark Materials, or the dark matter entities in Stephen Baxter's Zeelee sequence. When the math becomes this malleable, are physicists in danger of chasing a mathematical ghost simply because the chalkboard equations allow for it?
That underlying tension is the lifeblood of theoretical physics. History is fraught with theoretical ghosts that turned out to be the fundamental building blocks of reality. Paul Dirac predicted antimatter mathematically years before the positron was discovered. Wolfgang Pauli proposed the neutrino strictly to save the conservation of energy in beta decay, a particle so ghostly he famously lamented that it could never be detected.
Both were right.
Both were right. But history also holds phantoms like the luminiferous ether, mathematically theorized to carry light waves until relativity proved it non-existent. The pursuit of dark matter is not blind faith. It is an adherence to a robust, interlocking framework of independent observational pillars that elegantly explain a universe that would otherwise tear itself apart. We have mapped its shadow across the cosmos with exquisite precision, even if the object casting it remains just out of reach.
And that brings us to the profound synthesis of this epic journey. Dark matter is not a failure of human understanding. It is the invisible, heavy foundation of our very existence. From Lord Kelvin's blackboard in 1884 measuring the vertical drift of stars, to the James Webb Space Telescope peering into the dawn of time in 2025 to find primordial leviathans, we have definitively mapped the shadow.
We know its exact weight, we know its cosmic shape, we know its thermodynamics, and we know its history. We just don't know its name yet.
It is a remarkable testament to the audacity of human curiosity. We are an anomalous 5%, brief sparks of luminous chemistry, looking out into the cold void, demanding to understand the 95% that governs us.
Absolutely.
To leave you with a final mind-bending thought to mull over, the source material touches on the concept of complex, dark sectors that possess their own fundamental forces. If dark matter doesn't interact with our electromagnetism, we can't see it. But what if it interacts with itself?
A dark electromagnetism.
Exactly. What if there is dark chemistry, forming complex dark structures, occupying the exact same physical space we are right now? They wouldn't be able to see our light, just as we can't see theirs. To them, we are the bizarre, invisible 5% anomaly. Maybe as we look out into the void searching for ghosts, we are actually the ghosts haunting someone else's universe. Think about those streetlights in the dark city we started with. Maybe the city isn't empty after all. We're just fundamentally blind to the building standing right beside us. Until next time, keep diving deep.